Okay, we may start with the second part of the lesson. And in this case, I would like to discuss what happens when another field is applied to the electron system, not an electric field, but a magnetic field. And in this case, we suppose that the magnetic field is applied along one direction, and this direction may be the Z one. So the equation of motion for the wave vector is minus C velocity vector product B, and as the velocity is the gradient of the energy, what we have here is that when during the motion of K prime, the motion of K prime takes place in a plane that is orthogonal to B, because when you make the vector product, the result is orthogonal to B, and is also orthogonal to the velocity. As the velocity is the gradient of the energy, being orthogonal to the gradient of the energy means being on a surface, on a trajectory where the energy is constant, as you move always orthogonal to the gradient. So in case you have a, let me see if I may write down. No. Yeah, so if you suppose again to consider just the Fermi sphere, if B is applied along the vertical direction, and if you suppose that the, let's say, initial level is there on that point, then to understand what is the trajectory corresponding to that wave vector, you have to make an intersection between the sphere and the plane that is orthogonal to B and crosses the sphere in that point. So you make the intersection between this plane so you have the trajectory will be on that circle, and if you make the cross product, in this case the velocity is outward as the gradient points out of the sphere, then the B points upward because that is parallel to the Z direction. So in principle, the vector product should be going into the blackboard, but due to the minus sign, the opposite direction is fine. So the trajectory goes in this direction. Let me check. See, yes, velocity B, yeah, goes in that direction. And at that point, the electron moves on an energy where you have, on a surface, in this case on a circle, where you have a constant energy. So this is the trajectory you expect to have on the reciprocal space. Now the idea is to have some indications concerning what happens in the real space, because in general, when you consider a charge moving into a region where the magnetic field is uniform, you expect to observe a circular trajectory. So the idea is just to see what happens in this case when we consider an electron that is not free in free space, but is found within the solid. To make this connection, it's just useful to rewrite velocity as just the derivative of the position vector. So here we have that h bar k prime is minus E derivative of the position vector, vector product B. When making this product, I just wrote here the matrix. So we have I, J, K, then the three components of the vector are r prime x, r prime y, and r prime z, and then we have 0, 0b, that is the applied field, the applied magnetic field vector. So in this case, we have minus c, and then if you don't mind, I write the three components in using the notation where I have the parentheses and the three components of the vector within. Or I may also use the versors, so maybe it's easier to read. So I have I versor derivative of ry times b, and just to distinguish that this is not a vector, I put the modulus. Then I have versor j, and in this case I have minus rx derivative times b modulus, and no z component. So if you notice here, you have something where you combine the y and the x component, sorry, the derivative of the y and of the x component of the position vector. But in this case, you have not something that resembles nor the derivative of the position vector or minus the derivative of that vector, because you are mixing the components and you have also different sign of the components. So to switch the order of the components and change the sign, the solution that is used is to make a vector product with the b versor. So the solution to solve this problem is to multiply all the two sides of this equation by the vector product with b versor. So, and here we have minus e, and then b versor vector product I r prime y modulus of b minus j r prime x b modulus. And when we make this product using the same method, so we have I, j, k, the three components of b are 0, 0, 1, because we have just the versor, and then we have r prime y b modulus minus r prime x b modulus and 0. So in this situation, we have minus c, and then the first component is plus r prime x b modulus e versor. Then we have the j, where we have plus r prime y b modulus j versor, and then the third component is again 0. Just to write in a more compact way, here I have minus e, then I have b modulus in both terms, so I may collect b modulus. Then I have the derivative of rx, the derivative of ry. So I have the derivative of the position vector, but just in the xy plane. Due to the fact that the xy plane is the plane orthogonal to z, and z is the direction of the magnetic field, this combination is called the derivative of r perpendicular, where perpendicular means perpendicular to the magnetic field. Sorry, in the plane perpendicular to the magnetic field. At this point, what is generally done is just to say that if the derivative of k times this vector product is equal to a coefficient times the derivative of the position vector, then we may integrate the equation and have k of t minus k0 is equal to minus e b r perpendicular at time t minus r perpendicular at time 0. So at this point, we have a connection between what happens in the direct space and what happens in the reciprocal space. So the receipt is if you have the trajectory in the reciprocal space and the trajectory is given by kt minus k0, take that trajectory. What happens if you make the vector product by b? The vector product is just a rotation, because if you have the vector k and you make a vector product with b, you have a new vector that is orthogonal both to b and to k. So, and that happens for any value of k. So you are just rotating by 90 degree the trajectory. So this is this product here is a rotation. Sorry, is the 90 degree rotation. So the idea is take the trajectory in the reciprocal space, rotate the trajectory by 90 degrees across the direction of the magnetic field, and you have the trajectory in the real space. If the intersection between the, let's say, plane orthogonal to B and the constant energy surface is a circle, as we have here in the reciprocal space, then you have that the orbit of the electron in the real space is also a circle. So that is what you expect for an electron in free space. But what I would like to do now is just to present you a couple of situations where this is actually what we find, but the situation may also be different is the Fermi, in case the Fermi energy is more complex. So what I would like to do now is just to show you some real situations of Fermi energies to see whether the situation is always like that or not. So for those who are connected, now I'm going to stop the presentation. Okay. And I just switched to the full screen. Why two screens? Oh. I just ask to those who are connected, are you able to see my desktop now? Okay.
Yes.
So this is the, yeah. This is the case of lithium. So this is the result of the evaluation of the Fermi surface in case of lithium. Lithium is a metal that has a BCC structure, so that's why you see that this, what you see in white is just the first Brillouin zone. So that is the structure of the zone that is, let's say, the as the BCC lattice in the direct space has an FCC lattice in the reciprocal space, that is the first Brillouin zone of the symmetry corresponding to an FCC structure. As you see here, the let's say the color on this structure represents is just a color coding to distinguish the energy. So red means slightly lower energy, blue means slightly higher energy. We may also switch to I know, just in grayscale. Yeah, or this is just relating to the Fermi velocity. So just a slightly higher velocity here, lower velocity here. So apart from that, what you see is that even if this is not a perfect sphere, that is something that is very close to a sphere. So that's why when Drude and co-workers made the experiments at the beginning of the previous century concerning the properties of alkali metals, because lithium is in the first column of the periodic table, they found out something that was very close to what was predicted by the theory, also by the Sommerfeld theory, because this is actually a metal that can be well described by the free electron approach, as you see the structure of the Fermi surface is very, very close to a sphere. So when yeah, let's see the section. Yeah, if you make here, there is an intersection between, you see that in gray, this is a plane that intersects the Fermi sphere, and what you have, let's see whether, yeah. In this case, what you see here is just the path, the trajectory corresponding to the intersection. So this is very close to a circle. So in this case, again, what you expect is that when you switch from the reciprocal space to the direct space, then you find again this that the orbit of the electron is a circle or very close to a circle. The situation is slightly different if you consider another, yeah. This is gold. Gold is an FCC metal. So the lattice of gold is an FCC lattice. When you switch to the reciprocal space, you have a BCC lattice. So you notice that the structure of this Brillouin zone is different from the structure of the previous Brillouin zone. In this case, if you notice, you have let's say you have a distortion of the spherical shape, and that distortion, if you notice here, is when the surface joins the Bragg plane. In that case, you have that the surface is orthogonal to the plane when the surface reaches the plane, and in this case, you have the appearance of what is called in general a neck. So here you have many necks, and you have one neck each time the surface is close to one of those hexagonal sides of the first Brillouin zone. So the appearance of the neck is due to the distortion of the Fermi surface that is due to the interaction between the surface and the Bragg plane. In this case, if I show you again the intersection, we have two situations, and I need those two situations for the following of the lesson, not today, but also the next week. If you notice here, in this case, yeah, in this case, the intersection is not a circle, but is a closed surface. So it's something that is not purely a circle, but resembles a closed trajectory. So you have a closed trajectory in the reciprocal space and a rotated closed trajectory in the real space. So what changes is just a small detail concerning the actual path of the electron, but no big change concerning the shape of the trajectory itself. If you change here I've changed the orientation of the plane, so I have an intersection that goes through the necks. Now, if you notice here, the trajectory is not only in the first Brillouin zone, in the sense that the intersection here is within the zone. So as it happens, the intersection is always within the zone. But in this case, you have the opportunity to connect the first zone with the second zone. So if one electron is following, for instance, this path, is moving here, then this electron has access to the next zone, to the second. So in this case, the difference between these two situations is labeled by saying that in the first case, you have a closed orbit. So whatever the shape, the orbit is always within the first zone and is a closed orbit. In this case, what you have is the so-called open orbit, where open means the intersection is again within the first Brillouin zone, but if you follow the orbit, you have the opportunity to change zone. So in this case, you may, the electron that is traveling and along, for instance, this branch of the intersection, if that electron follows the path, then in principle, the wave vector may exit the first zone and reach the second one. And so that's why this structure is called open orbit. So for what concerns the description of the effect of the magnetic field, I will refer, I think not today, but next Monday, to the distinction between open orbits and closed orbits. And I just wanted to let you see something else, and this is the following. If we go back to the case of lithium, so lithium is a free electron metal, so nearly spherical Fermi surface. Now, it is possible, if you look here, you have written Fermi energy 0. Fermi energy 0 means, doesn't mean that the Fermi energy is 0, but means difference between the Fermi energy you are representing the diagram and actual Fermi energy. So the fact that that is 0 means that what I'm seeing now is actually the structure of the surface that corresponds to the Fermi energy of lithium. If I increase that value, you see that you have the appearance of necks also in this case. So what is the conclusion? In principle, now I'm looking at the surface of something that is not a free electron metal, because here I have a strong distortion with respect to the free electron case. So the idea is the fact that you have a free electron metal doesn't mean that the gap is 0 or that the Bragg planes have no distortion. The fact that you have a free electron metal just means that due to the electronic density that you have in the system, the Fermi surface is not large enough to feel the effect of the distortion. So in principle, you may have that in lithium, the gap is maybe also as high as 1 eV, so a very strong gap. But the fact that you have a small number of electrons, so the Fermi surface is small, the Fermi surface is not large enough to reach the border of the zone. So the Fermi surface feels no distortion. So the fact that you have a free electron metal or not is not an effect of the strength of the effect of the Bragg planes, but is mainly related to the electronic density. So in general, if you have a system with a small electronic density, then maybe you have a free electron metal. If the electronic density is very large, then the possibility to have a free electron metal is nearly 0, because high density means huge spherical, huge, let's say, Fermi sphere. Huge Fermi sphere means that the sphere is not just within the first zone, but reaches maybe the second, third zone. So at that point, you have a strong distortion. So again, the effect of having free or non-free electron metal is not just something that is related to the intensity of the gap. It's something that also includes the contribution of the electronic density. And just to let you see something that I will, let's say, never been able to obtain analytically here or with the drawing, is a situation where we have a large number of electrons. For instance, if you consider transition metals, and transition metals are in the central part of the periodic table. First, for instance, first row, when we have iron, chromium, manganese, nickel, cobalt, and copper, and so on, in that case, you are filling the D levels. The D levels, unless you consider copper, are not completely filled. So you have that the number of electrons that be considered for the calculation are not just one, but you have a number that ranges from 1 to 10. So you have the opportunity to have a great number of electrons to include in the calculation. And here I just show you what happens for iron. I hope to show you what happens for iron. No, ieri l'ho provata 3 volte. Okay, let's try again. So in this case, if you notice here, you have band 0, band 1, band 2, band 3. So this means that the the occupied levels are found in 4 different bands. So this means that if you start from the, let's say, the sphere, and then you introduce the distortion of the lattice, those distortions are so strong that the electronic levels occupy 4 different bands. So you have a huge number of electrons, so 4 bands that are interested by the electronic population, and it's also possible to see 1 band at a time. So this is just the first band. That means that the first Brillouin zone is nearly occupied by levels, and you have just this 6 portions where you have, let's say, here within the portion you have 3 levels, and in the rest of the zone you have occupied levels. So here you have just a small number of 3 levels. Then if you switch to the second band, then you have these large regions here and also these small corners here. Then you have the contribution of the third band, and then the fourth. The fact that you have these structures with particular shapes is due to the fact that in the first zone, if you consider the intersection with the first zone, then what you have in the first zone that here is called 0 is what you actually see in this plot. But if you consider second, third zone, and so on, then you have to pick all the intersection and translate back in the first. So that's why the structure that you have at the end is more complicated. So this is just to say that in situations where you have that the number of electrons is large, the opportunity to find what is a free electron metal then is nearly low, very low. And just to have a sort of overview of what is the situation, we may look at this diagram. This is a sort of periodic table where you find the Fermi surfaces of the metals. As you see here, for alkali, you have a nice situation where they are nearly spherical, apart from cesium, the last one, where maybe due to the fact that let's say, the electronic density is more or less similar because they just share the one s electron. But what changes is also the lattice spacing that determines the size of the zone. So as the size of the zone changes with the lattice, maybe if the lattice spacing is different here, you may have this you may justify this slight distortion here in cesium. Then as soon as you go to earth alkali metals, that means 2 electrons shared with the system for the formation of the metal, then you have that the structure is really more complicated. And even worse is the situation here, where we have transition metals. As we will see later, the situation is slightly better if we consider noble metals, because for noble metals, you have that the 3D levels are filled and you have just one s electron. So in this case, the noble metal is the situation where we have filled bands, the d bands with 10 electrons are filled, so those electrons do not, let's say, are present into the system, but I will show the diagram later, they do not reach the Fermi surface. So at that point, the Fermi surface is not exactly equal, but close to the Fermi surface of the alkali, because in both situations, both alkali and noble metals, you have just one electron that is, the density of the levels that appear at the Fermi surface is supposed to be low. So in general, you expect to have a small distortion. This distortion anyway produces what you see here. That means the different necks for the for the noble metals. Let's say this is just a web page. So I will put the address if you want to have a look to the structures. Then if you click on the element, then you may download the structure and look that on your PC. If you have Windows or Mac OS, then there is a plugin for the browser, so you may look at those directly into the browser. And differently, if you want to, let's say, see those plots here, this is just a free program to look at the Fermi surfaces. I will put the web address where you may download that. Also the different Fermi surfaces of metals or also compounds. So in that case, you may have a look at the different situations. So this was just to, on one side, compare the different shapes and bring it to your attention the fact that in general, irrespectively of the shape of the Fermi surface, we may have at least two groups of trajectories. One is closed orbits, so when the intersection is completely within the first Brillouin zone and no contact with the border of the zone, or open orbit, when we consider that the intersection crosses the Bragg planes, so in a continuous way, the equation of motion of the wave vector may bring the initial value of the wave vector to a zone that is not the first zone. Okay, so I just wanted to distinguish that. Now I switch to the... do you have questions or comments? Were you able to see everything from home?
Yeah, we did.
Okay. Now I removed this, the desktop sharing, and I switched to the sharing of just the yeah. Okay, so going on to the okay, I hope in a while I will be able to recollect. Okay. Yeah. So in general, the idea is the orbit may be slightly more complicated with the actual orbit you expect to find in case you consider the empty space. I just would like to make one last calculation, then I stop. And the calculation is the following. In general, when the when we consider an electron in free space, we have that the motion of the electron due to a magnetic field is described by a circular motion, and we may define the cyclotron frequency, that is a frequency that indicates how fast the electron travels through this circular orbit. So due to that, it's possible to define the period, so the amount of time that is needed by the electron to travel through the orbit. So the idea is, in case, let's say, it would be nice to have the equivalent of that corresponding to the actual orbit of the electron. So the question is it possible to estimate the period of the orbital motion of the electron while the electron moves in this orbit that may be a circular orbit or a closed orbit with the deformed structure with respect to the circular one, or also an open orbit. So the idea is, let's just try to evaluate the time needed to travel through a part of the orbit. Then if the orbit is closed, then we may evaluate the duration of the full path, and then we have the period. So the let's say maybe the three-dimensional plot is not, I'm not able to draw a full three-dimensional plot. So what I would like to plot here now is just the path of the orbit of the electron in the plane that is orthogonal to B. So I suppose that B is always parallel to the Z direction. This is a plane orthogonal to B. This is just a portion of the intersection between the Fermi surface and this plane. So the starting point, so K0. So K0 is there. And what I expect is that K0 will, starting from K0, the equation of motion of the wave vector will take that wave vector along the path, depending on the strength of B and the shape of the surface. So what I expect is that we will have a motion of the wave vector along the trajectory, and at some point we will reach a point K1. So for the moment, K0 and K1 are arbitrary points. K0 is just the starting point of the trajectory. K1 is an intermediate point. In case the trajectory is closed, then at some point K1 will reach again K0, so we have a closed orbit. So if we define delta T as T1 minus T0, we first try to evaluate delta T, and then from the expression of delta T, we may eventually obtain the value of the period. And in this case, to evaluate this difference, the starting equation is just the this definition, if you take the modulus, I just write, let's say in general, when you allow a small variation of t, in general, the variation of t is positive. So that's why I do not write the modulus sign across dt. So due to that, we may say that dt is dk modulus divided by k prime modulus. So delta t can be expressed as the integration from t0 to t1 of dk modulus divided by k prime modulus. As the trajectory is the trajectory that is described by the wave vector when you have just the magnetic field applied to the system, k prime h bar k prime is equal to minus c, the velocity, and the velocity is the gradient of the energy. So we have h bar gradient vector product B. It is possible to rewrite this equation as minus E divided by h bar. If you keep B fixed, so if B is, let's say, if we try to estimate the result of the vector product, the result is in general product of the modulus of the first vector, modulus of the second vector, sine of the angle between the vectors. So here we may write B modulus, and then what is left regarding the gradient is just the component of the gradient that is in the plane orthogonal to B, because the component of the gradient that is parallel to B gives us a vector product that is 0. So here, instead of writing modulus of the gradient times sine of the angle, I just write component of the gradient orthogonal to B. So here I write gradient orthogonal. That means only the component of the gradient orthogonal to B. So this component can be plotted in this plane because that is on that plane. So the component, the perpendicular component is exactly in that plane. At this point, I may substitute the expression for k prime into the integral. So this is equal to the integral from t0 to t1. We have dk modulus. Then I have h bar square at the denominator. Okay, then I have E positive because I consider just the modulus. Then B, and then I have the gradient the component of the gradient that is perpendicular to the magnetic field. Now, if you look at the gradient points in a direction that is orthogonal to the trajectory. So if you suppose to move along that direction, I just make an expansion of this part. So if this is the trajectory, this is k0 or an arbitrary point of the trajectory, the component of the gradient is orthogonal to the trajectory. So if you make a small variation in that direction using a vector that is called, that I call just delta k. So delta k is just this small vector. if you move along delta K on that direction, what happens? You reach a second constant energy surface that does not correspond to the initial energy, but corresponds to an energy that is slightly different from the initial one. So this is I call that, let's say, E0. So the energy that the electron has during the motion, and this is E0 plus delta E. So if you move along that direction, you may reach a second constant energy surface that corresponds to an energy that is slightly larger than the initial energy. So what we have is that the energy variation between the initial constant energy surface to the new constant energy surface can be written as the gradient of the energy perpendicular times delta K. Due to that, I may replace the expression of this gradient using delta E and delta K into the integral. So this is equal to the integral from T0 to T1 of dk modulus h bar squared divided by EB. And then in place of the gradient, I write delta E and delta K. At this point, I may take out of the integral all the constants. So I have h bar squared EB, and also delta E is not, let's say, is out of the integral, because delta E is just the energy difference between the initial surface and the second surface. So I may take also that out of the integral, and then I have T0, T1, dk modulus and delta K. If you notice now, this integral is the summation of the product of delta K modulus, dk modulus times delta K from the initial point to the final point. If you look at this diagram, dk is along the trajectory. Delta K is orthogonal to the trajectory. So dk times delta K is the area of this rectangle. And as the electron, as the level moves along the trajectory, you always consider dk and delta K, so a new rectangle, dk and delta K, a new rectangle. So what you are evaluating is the area variation between the initial surface and the second surface. So this integral is equal to delta A, where delta A means the areal variation between one energy surface and the next, divided by delta E. That is the energy variation between the first surface and the second surface. In case, and this is, squared. Now, if you compare this, now in case the orbit is closed, if T1 is equal, in case the orbit is closed and you make the integral across the orbit, then this expression represents the period. So that should be, not should be, but that may be compared to the free electron case. One always tries to make this comparison. That is 2 pi times m divided by EB. So this, if the orbit is closed. Because only if the orbit is closed, you may define a sort of period. So if you notice, you may find an expression for m, and this expression for m is h bar squared divided by 2 pi areal variation divided by energy variation, because EB and EB are found in both on both sides. And so this is a way to define a new value for the effective mass of the electron. Yeah. Oh, I'm sorry. It's 8 past 11, so it's better for me to stop here, because then you have to follow the lesson of quantum mechanics. So I will add an additional comment about that just on next Monday. So I think I will stop here. Do you have short questions or comments? Also, those who are connected have questions or comments. Okay, if you have no questions, then I switch off